So this is video problem 7, where we are looking at a spherical capacitor and we would like to derive its capacitance and stored electrostatic energy. So here we have our spherical capacitor configuration. It consists of an inner conductor which has a radius A and a total charge plus Q. And also we have the outer conductor that you can see here, and its radius is equal to B, and it will carry a total charge minus Q. The space in between is occupied with a simple dielectric material with this permittivity epsilon, so that we have this simple relationship in the dielectric between the D field and the E field. So because of the spherical symmetry and what the implications of spherical symmetry are, you can also review in all details in video problem 1 and video problem 4, but this essentially would imply that the charge will be uniformly distributed on the surfaces of inner and outer conductors. So the surface charge density at the surface of the inner conductor is simply the total charge plus Q divided with the surface area of this conductor that has a radius A, and this would then be the surface charge density on the outer conductor, where the term in the denominator is the surface area of the outer conductor. Because of this, uniform charge distribution, which is illustrated here by these positive charges on the inner conductor and the negative charges on the outer conductor, the electric field will have this particular direction, so it will be in a radial direction from the inner towards the outer conductor. And of course the field orientation of the D field will follow the orientation or the direction of the E field. If we introduce our rectangular XYZ coordinate system with the associated spherical R theta phi coordinate system as shown in the figure, this implies that our electric field will only have a radial component, and the magnitude of this radial component will only depend on the distance to the observation point in the dielectric material. And of course the same will hold true for our electric flux density or the D field. So we now proceed with getting the capacitance of our spherical capacitor, which is also included in the figure on this slide, and this is the general expression for the capacitance, where V0 is of course the potential difference or voltage between the positively charged conductor and the negatively charged conductor. This is the form of the electric field intensity, and this is the form of the electric flux density, and these fields are also illustrated by these red vectors in our dielectric material. Because the D field only has an R component, and this R component only depends on the distance, we can conceive a spherical Gaussian surface with radius R as shown here, and you can easily see that everywhere on this surface the D field will only have a normal component, and this normal component will be constant. That means that we can use Gauss law, which is stated here, which simply says that the flux of the D field through a closed surface S is equal to the total free charge enclosed by the surface. So it's a very straightforward application of Gauss law to this spherical Gaussian surface that will give us the required D field. So these are the limits of our surface integral. So we are essentially integrating over the surface area of this closed spherical surface. So phi is going from 0 to 2 pi, theta is going from 0 to pi. This is our D field, and this is our standard ds element for such a Gaussian surface. For a detailed determination of this ds element, I refer you also to video problem 1 and video problem 4. The left hand side here is of course equal to the total free charge enclosed by the surface, and this is exactly the assumed positive plus Q charge on the surface of the inner conductor. So this Gauss law immediately gives us the surface area of this Gaussian sphere times the magnitude of the d field, that is equal to the total free charge enclosed. You can easily isolate the d field and also write it in this vector form that you can see here. So this is the electric flux density in the dielectric of our spherical capacitor. Because the material is simple, this relationship will hold between the d field and the E field, so it's very easy to determine the E field once we know the d field. So this will be the result for the electric field intensity. And now you can see from this general relationship here that we would need to determine the voltage between the inner and outer conductors. This is the line integral of our electric field from R equal to A to R equal to B. This is our electric field intensity, and this is our dl element. So from this integral we first take the constant that you can see here outside, and the rest is actually to evaluate the integral of 1 over r squared, and this is easily done so that we very easily arrive at this final result for the voltage between the inner and outer conductors. Now we can take of course the assumed Q and divide it with our voltage down here to actually arrive at the final result for the capacitance of our spherical capacitor that you can see here. As was the case for parallel plate capacitor and also our coaxial cable capacitor, and in fact any other capacitor, the capacitance of our spherical capacitor only depends on the material properties of our dielectric material, which is the epsilon permittivity that you can see here, and also the geometry of the capacitor, i.e. what is the radius of the inner conductor and what is the radius of the outer conductor. So we would next like to determine the energy stored in our spherical capacitor, which is also repeated on the figure included in this slide. The energy can be determined by the expression here, which is 1/2 the volume integral of this dot product of the electric field and the electric flux density. You can see the expressions for the two fields down here. So the dot product is given by the expression here, and it is seen to be a function of the radial coordinate only in the manner shown over here. So the volume integral is of course throughout the volume of our spherical capacitor, which is essentially integrating over the volume of the dielectric where the fields exist. So that will be in the radial coordinate going from the inner to outer conductors, phi going from 0 to 2 pi and theta going from 0 to 2 pi. What we have here is the standard differential volume element in spherical coordinates. Because the integrand is independent of phi and theta, the integrations in phi and theta are straightforward and they will give us 4 pi. So the rest is actually to evaluate this single integral along the radial direction. When we plug our integrand in our expression, our integral expression, we arrive at the result that you can see down here, and this is easily evaluated to give us the following expression for the stored electrostatic energy in our spherical capacitor. So this is the result that we wanted to derive for the energy stored in our spherical capacitor. We may recall that the knowledge of energy will give you an alternative approach to obtain the capacitance of our capacitor, and this is the general relationship linking the electrostatic energy with the capacitance. and we can plug our derived expression for the energy, which is seen here, in our expressions over here to rederive the result for the capacitance of our spherical capacitor, which of course resembles the one that we derived on the previous slide. So we are now essentially finished with all our tasks, and you can see the summary of the main results for the capacitance and stored electrostatic energy. And we would like you to check the units for this capacitance and the derived electrostatic energy. We would also like you to use the appropriate fields to determine the surface charge densities which will be induced on the inner and outer conductors of the spherical capacitor. So use the fields and the boundary conditions to this end. And we would also like you to show that the above capacitance will take the form of the parallel plate capacitance when A is sufficiently close to B. Thank you very much for your attention.